my name is Sophia Lynn, and this is Physics 2212 Lab 3 Circuits. The purpose of this lab was to use the principles of energy conservation to predict the behavior of circuits with resistors in series and parallel. By utilizing multimeters, we examined the behavior of resistors and capacitors. The fundamental principles we used was Ohm's law and Kirchhoff's loop and node rule. In a quick preview of the results, we found that the node and loop rule held true and that the current was found to be 0.0205 amps. So the first fundamental principle we used was Kirchhoff's node rule, which says that the current entering a node equals the total current leaving the node. The loop rule tells us that the sum of potential difference around any loop is equal to 0, and Ohm's law states that voltage equals the product of the current and resistance. First, by utilizing Ohm's law, we predicted that the current through the circuit was 0.0205 amps, and after assembling the circuit, we verified our prediction by finding the ammeters readings. And when we reverse the connection, the current becomes negative, but the same magnitude. Second, we converted one of the ammeters to voltmeters, and we found that the voltage was 3.2 volts, and the ammeter becomes 0. This is because the voltmeter has such a high resistance that the current basically becomes 0 in the circuit. We then measured the potential differences across each circuit element and found that the potential difference between the battery was 3 volts. For the 47 ohms resistor, it was negative 0.9 volts, and for the 100 ohms resistor, it was negative 2.1 volts. Therefore, that summing all of those together, we get 0 volts, which proved that the loop rule is true because the sum of all of the potentials in our circuit should give us 0. This is our graph that we saw, and with all of the voltages and the resistance, we see that it drops down to 0 after the 100 ohms because that completes the loop. When reconnecting the voltmeter across the 100 ohms resistor, we found that the current was 0.12 amps, and we replaced with an ammeter in parallel, we get a current of 0.056 amps. This is because the ammeter has low resistance, therefore the path of the circuit will go through this instead of the 100 ohms resistor, and the circuit always wants to take the path of least resistance. Finally, this is us finding the resistance of each of the element in our circuit by using Ohm's rule or Ohm's law. So for the 47 ohms resistor, we did 0.9 divided by 0.0206, which equals 43.69 ohms. For 100 ohms, we did the same thing, got 101.94 ohms. For the wire, it was 0, and for the ammeter, it was also 0. For our RC circuit, we found that the light bulb dims while the capacitor charges and discharges, and finding the exact times we can find the value of RC, which was found to be 5.9. Note that we didn't have time to do this in our lab, so the graph that is shown here is actually from the PhET simulation. The predicted RC is 30 ohms times 0.2 Faraday, which equals 6, and then our experimental that we found using PhET was 1 over the slope, which gives you 5.9, so it's pretty close. So there are probably two sources of error. First was just a simple measuring error where we couldn't get exact data, and also from outside sources, other things could be affecting our circuit, such as static, and other outside forces that could have caused our information to be a little bit incorrect. And what if we charged a capacitor with no resistor in the circuit? If there was no resistance in the circuit, then the capacitor would be charged immediately. However, this would not happen in real life because batteries and wires inherently have a little bit of resistance to them.